All right, so the next chapter is gas laws, which means I also have to figure out where I put my file. All right. We talked about the gases a little bit in chapter 1. We did some really basic concept stuff in chapter 1, some sort of almost middle school level of talking about them. The main focus of the chapter 1 information there was that when you have gases, they don't have a definite volume. Okay. You can squish them. If you have lower pressure, they will expand. They can fit in a lot of different places. They also have no definite shape. Doesn't matter whether you're putting it in a scuba tank or in a Mickey Mouse shaped balloon. Okay. They will assume the shape of their container. So those two ideas kind of move forward and turn into 4 more properties that are sort of directly related. We have their ability to uniformly fill any container. All right, so my glass of pink lemonade. So my container, my liquid is at the bottom of the container, okay? The air is obviously above, okay? If I had a sample that was entirely gas, obviously its ability to float up out of the container would potentially be a problem. But gases are often in capped or sealed containers, and so they expand to fill them. You can compress them. So if you happen to own an air compressor, okay, whether it be for using on your power tools or filling your air mattress, the idea is that you can force air into a closed system at pressure, okay? If you want to fill your tires, okay, if you go to Wawa, okay, and use their air compressor to top off your tires have a higher pressure than regular old air pressure. And so they are compressing the molecules as they are being put into the tire. The other thing that people often kind of forget is that gases can mix with each other without a lot of effort either, okay? If you own those, what do they call them? Glade plugins, which I think usually smell horrendous, but some people like them. And you plug it in and you walk all the way to the other side of the room. The first 5 minutes, you can probably barely smell it. But given another hour, you could probably walk anywhere in the room, and including possibly into neighboring rooms, and be able to smell the scent, because the little bit of liquid that comes in those things has been vaporized into a gas, which then spreads. They also exert pressure on their surroundings. So here, sitting in front of my computer, I am being squished upon by air pressure because there is an atmosphere above us as well as around us. All right, we need to have some ways to measure pressure and describe it. So if you think about this from a a little bit more generic point of view, maybe more physics point of view. It will talk about pressure as force exerting against an opposing body. Okay, force per unit area. So if you take your hand and you push it down on the tabletop, okay, you are exerting pressure. The unit area being the contact space between your hand and the table. So pushing out, pushing down, pushing up also qualifies, especially when we're talking about gases, because they are usually in a closed container when we are measuring them as far as chemistry is concerned. If you pay attention to the weather, you can tell something about upcoming rain and upcoming storms by looking at the barometric pressure. So Tuesday, when I was driving back from the beach, I go to physical therapy down toward the ocean front, and right about 3 o'clock, okay, the barometric pressure took a dive about 15 minutes before the rain started. You can, some of us are sort of more sensitive to it than others. We can kind of feel the pressure change. But there are ways to measure it. And that also goes into one of the facets of how weather prediction, weather forecasting actually comes into play. So we are going to look primarily at 3 different units. Now, 2 of them tend to get used a lot more than the other one. I just realized I misspelled atmosphere. No, actually, I didn't. Yeah, I did. I have the wrong O in there. So the first one is called millimeters of mercury, Hg for mercury. But you will also see it referred to as Tor. More famous dead guys. Torricelli, being a guy who lived in Central Europe, actually near the base of a mountain. And one of the things that he discovered in his studies was that the pressure on his bucket of mercury and the glass tube he had stuck in it was different at the bottom of the mountain than it was at the top of the mountain. Okay. So hence we kind of use a version of his name as one of these units. Atmospheres is another unit. So this is tidewater. We are essentially at sea level, or a couple of feet above or a couple of feet below in a couple of spots in Norfolk. If we took the pressure at ground level, okay, averaged out over an entire year, that's basically how they decide what 1 atmosphere of pressure is. Now we need to be able to do conversions. So 1 atmosphere is 760 torr, otherwise known as millimeters of mercury. This is one that you are going to use or going to see quite a lot of. And more bad spelling errors. The other one that is actually the SI unit, however, truthfully, the only people that I have seen use it career-wise on a regular basis seem to be the pulmonary/respiratory field. If you are going into respiratory therapy as a career path, and you are reading information about like how to set ventilators and things like that, that is one of the few situations that they tend to reference pascals quite more often than kind of any other medical field. Pascals are tiny. Pascals are super tiny. 101,325 of them in one atmosphere. So even though millimeters of mercury are kind of small, pascals are much smaller. So I want to give you some examples here to go back and forth, but I also want to momentarily talk about we'll call it the everyday unit, especially because this is the US and we have not caught up with the rest of the world in terms of metrics. If you are measuring the air pressure in your tires, and you look on the booklet that came with your car, okay, that tells you, oh, how many PSI your tire pressure is supposed to be. PSI, pounds per square inch. So here in Tidewater, at ground level, that means every single square inch of your body is being squished on by 14.69 pounds of pressure. Think about this in terms of the fact that we have several miles worth of atmosphere above us. And even though we don't tend to think of it on a daily basis, air has weight. Okay, air is a gas. Granted, air is a mixture. It's lots of nitrogen, some oxygen, and traces of other things. But it is matter, and therefore it has weight. All right, how about some conversions? We need to kind of swing back to, again, some of the things that got kind of touched on in the first chapter in terms of how you're doing your conversions. If we want to go from 665 millimeters of mercury over to atmospheres, remember, thing you are looking for goes on top. Thing you are trying to cancel out goes on the bottom. So I am dividing by 760. And my 665 millimeters of mercury will become 0.875 atmospheres. So a little less than 1. How about pascals to torr? Now this ties 2 separate pieces of information together. Okay, kind of think of it from this point of view. Okay, when you're doing algebra, one of the things that they go through is if A equals B and B equals C, then you can assume that A and C are the same too. So it's kind of what we're doing here, because we saw that 1 atmosphere is 760, but we also saw that 1 atmosphere is 101,325 pascals. So we can set them equal to each other. Granted, it looks messier when you are crunching your numbers. You're going to take this massive amount of pascals, 2.1240 times 10 to the 6th, so we're talking in the millions, multiply by 760, and then divide by the 101,325. You will get 15,931 torr as your answer for this. All right, so some conceptual stuff, some basic measurements that we have not seen before, because up to this point we've been kind of focusing on such things as grams and kilograms and liters and milliliters. So this is a new unit for this chapter. A huge chunk of this chapter is tied into the idea of equations, relationships that occur between various parts of gas theory. All of them are named after yet more famous dead guys. Okay. The first one is named after Robert Boyle. Okay. He got mentioned oh so briefly back in chapter 2. And a lot of these equations have two versions. Often the first version, I'll kind of loosely refer to them as the theoretical version. It gives you a relationship, but it also then often throws a couple of constants in and kind of doesn't give you any way to change your data. So when we start with the theoretical version here of Boyle's law, so I've got P times V, so P for pressure, V for volume, equals a constant. Okay. I will also refer to this as the whoopee cushion theory. So you have the whoopee cushion and it's inflated. Okay. It has that little tube on one side. And if you sit on it, it makes the wonderful sound. Okay. But the reason I call it the whoopee cushion theory is if you sit on it, okay, therefore you are increasing pressure. And as it makes the really annoying sound, it is decreasing volume. And so you get this kind of upside down version or inverse relationship. When the pressure goes up, the volume goes down. If your pressure decreases, your volume increases. And yeah, I sort of referenced the frog in a bell jar. That's a really sort of bad traditional science joke there. If you look on, I think I actually put the links to these on the useful videos page. Actually, let me see if I can find this on my, so I can figure out if I actually remember to post this on my Canvas link. Because I think I posted 3 videos that are all tied in here to the gas laws. Normally I kind of show these in class and then we kind of talk about them, but that's always more problematic on Zoom. All right, back to, can I share this? Why is this being flaky? Hang on, this might take a couple minutes. My ability to share that is being less cooperative than I would like. I think I have too many windows open. Okay, so here's your interface here that has videos that are helpful. Okay, so there's a couple, but the ones that were actually from chapter 2, or chapter 1 and 2 and 3, and okay. So these are ones that you should actually go back and watch later. There is one here that involves Boyle's law, that involves putting peeps in a jar. There's one that involves the combined gas law, and there's also one that involves pressure and temperature. So Gay-Lussac's. So go back at some point and actually watch those videos. The first one especially is actually kind of fun. So let me talk though more about the Boyle's law relationship here. So a vacuum pump basically removes air from a container. So in this case, peeps, marshmallow peeps, are placed in this clear glass container. And because it has a pump attachment, the pressure within the jar is lowered. So much less than normal air pressure, which causes the peeps to kind of swell up. And then as the second half of the video, the air is allowed back into the container, and then the peeps kind of shrivel up as air pressure is reasserted. So this gives you some visuals to go with this whole inverse relationship idea. So now we get to what I will call the more useful version of the Boyle's law. This is the one that you use when you are actually doing the calculations. And note, it looks an awful lot like an equation we saw in one of the previous chapters. Instead of M for molarity, we are using P for pressure. So P1V1 equals P2V2. Okay, rules of algebra. If you only have one equation, you only get to have one unknown. So that means you have to know 3 of the things that you are putting into this equation. And I invented an example here to show you. So we have a 4-liter flask. Now, flasks for gas, unlike the flasks that we tend to use in lab, are structured a bit differently, and they have basically a lid to keep the gas inside. So we have a 4-liter flask, and we know the pressure is 680 torr. And more ridiculous typos. I'm going to squash it and make the volume decrease down to 3. I want to find out what the new pressure is. So think about this from a concept point of view, okay? Before I even start the math, I can kind of make a prediction. I decreased the volume, and I know that this is a inverse relationship, so I should expect to get a larger pressure than I started with. So plug in your numbers. 680 times 4, P times 3.0. Move your 3 to the other side so that your P2 is essentially by itself on the right-hand side there. Finish out your number crunching. 680 times 4 gives you 2720. Divide by 3, and you end up with 906.7 torr. So yes, I did in fact get a larger pressure because I decreased my volume. So as we are progressing through the chapter, you will see a whole bunch of different versions of how we're sort of manipulating pressures and volumes and temperatures and moles. Okay, so let's take about a 10-minute break, and I will come back and we will go on to the next law. before we get into Charles' law, are there questions about the first segment? All right, so we are going to move onward to the next relationship. All right, more famous dead guys. This one is Charles' law. This one is a combination of volume and temperature. Now, again, this is another one that starts out as this sort of theoretical relationship. We have volume being based on a constant value times temperature, okay? One thing that is true about the temperatures, and this is kind of all the way through the entirety of this chapter, is you must convert your temperatures to Kelvin. Okay, so again, there's some bits and pieces in this chapter which kind of drag forward into this one, from chapter 1 into this one. If you are converting from Celsius to Kelvin, you are adding 273. Okay, why? Because other units of temperature, both Celsius and Fahrenheit, are capable of having negative values, which would imply, if you tried to put them into your equations, would imply that you had negative volume. Okay, that's actually not allowed. You can't have negative volume. Black hole theory notwithstanding. If you put the wrong values in, it's even if they're positive, it's going to give you the wrong relationship. So we have to stick to keeping them in Kelvin. Now, this relationship is not an inverse one. This is a direct relationship. Okay. Think hot air balloons. So if you have your hot air balloon and the basket in the back of your pickup truck, and you unroll it and lay it out on a big field because you're going to take off. Well, in order to take off, you have to be able to puff up your balloon so that it will actually both inflate and then rise. Both of those are relationships that are tied into temperature. The burner that heats up the air that is going into your hot air balloon is expanding because you are heating it. If you have a decrease in temperature, you will get a decrease in volume. Think about it this way. If you have a half full water bottle and you jam it in your freezer because you're trying to cool it down before you go somewhere, and you forget it, you come back at the end of the day, it's probably frozen. It also kind of looks a little deflated, maybe even a little crushed inward, because as the air above your water cooled, it began to take up less space. So this is your direct relationship. So here's the useful version. Again, we have two sets of data. We have V's and we have T's. The left-hand side being V1s and T1s, the right-hand side being V2s and T2s. We are also making an assumption, and it's kind of an assumption we also made for Boyle's law. Boyle's law, we kind of made the assumption that we were not cooking it, changing its temperature at the same time that we were doing anything else to it. For this one, the assumption is that your pressure is not changing. So I gave you two different examples here. One of them uses Kelvin temperatures as the starting point, but then I also did a second example that did not have temperatures in Kelvin. So if I have 3.5 liters of gas, and we are at 305 Kelvin, that's going to give us a situation then that when we heat it up to 360, that we should expect a larger volume, okay? Because remember, if you're only dealing with two variables at a time, this should give you a situation where you can make some ballpark predictions. My temperature went up. My volume should go up. So I plugged in all my data, and then I used the methodology of cross multiplication. Yes, it is perfectly fine to do the more strategic rearrangement. However, I tend to teach this by giving examples that make use of the cross multiply method. I find that people are less likely to have errors if they use the cross multiply method. So I have 3.5 times 360 and 305 times my V, which technically is my V2. And crunch your numbers. I get 1260 on the left-hand side. I then need to move my 305 such that I'm dividing by it. And yes, I do get a higher volume as my new and second volume, 4.13. So it increased a noticeable amount because I heated it up 55 additional degrees. Now, here's the other one that I gave you your initial information in terms of Celsius. So I've got 5.1 liters, but it's at 120 Celsius. And I want to shrink it down to 4.3 liters. What's my new temperature? All right, so add your 273 to the 120, and I get 393 as my first temperature. So 5.1 over 393, 4.3 over T. But again, I can kind of make a prediction. It ought to be lower, okay? Even once I convert back to Celsius, it should be lower than 120 Celsius. So I went ahead and did my math. I did my cross multiply, 5.1 times T and 4.3 times 393. I multiplied my right-hand side. I moved my 5.1 to do my division step. And on the Kelvin end of things, I end up with 331.4. If I subtract my 273, my Celsius temperature is 58.4. Now, the next one, your textbook labels it something that I had never seen it called before. All the other textbooks that I've taught for in the past couple of decades refer to the pressure and temperature relationship as Gay-Lussac's, named after some dead French guy. It somehow gets labeled Amintons in your textbook. I'm not really sure. It doesn't actually affect how the equation works. It's just if you are looking for additional examples, you may have better luck Googling Gay-Lussac as a way to look for additional examples. Now, this one, like the Charles Law, is a direct relationship. P's and T's. If your pressure increases, it probably means your temperature increased. This is one of the reasons why it says don't throw the spray paint can in the fireplace. Okay, if you are increasing the temperature dramatically, it may blow out the can, okay, blow apart the can because of that pressure increase. This is also somewhat tied into the now couple of decades ago Challenger space shuttle explosion, because as the fuel was being vented during the burn, the pressure dropped dramatically, but that also meant the infamous O-rings, which were right at the place where the hole where the venting is occurring, also dropped dramatically, and the O-rings cracked and led to catastrophic failure. So there are some actual real world, applications to why we need to know this stuff. So this one, I kind of dramatically invented some data here, giving you a flask that starts out at a pressure of 15 atmospheres. Okay, that's kind of up there, but it was at room temperature, okay, 25 Celsius. If I wanted to drop it all the way down to 1 atmosphere pressure, what's my new temperature? So again, I'm paying attention to the fact that information was presented to me in terms of Celsius. So I need to add my 273 to it. That gave me 298. Do my cross multiply, do my final division, and I end up with a pretty tiny temperature in terms of Kelvin. I'm all the way down at 19.87 Kelvin. Okay, we're not down to absolute zero, but we're definitely deep space temperature. Okay, temperature outside our atmosphere. So back to space shuttle ideas. It's like some of that was out at the edges of our atmosphere because they were circling us in orbit. So it's not unrealistic to assume that the temperature might have been somewhat near 20 Kelvin. All right, Avogadro's. Mr. Avogadro, whose number we saw back in previous chapters. Now we're going to kind of revisit him again a little bit, but we're going to do this in terms of mole amount versus volume. More stuff takes up more space. Okay, makes sense. Again, we're kind of making some assumptions here. We're assuming that we are only changing one thing at a time, that our temperature and our pressure are constant. And so we can determine how much space a given number of moles takes up, providing we haven't changed the temperature or pressure. I gave you 0.35 moles, which takes up 8.4 liters. You don't actually have to know the temperature and pressure. You only have to know that they are not changing. How much volume will 0.48 of the sample take up? Set it up as a ratio. Again, we're dealing with a direct relationship. More stuff, more space. I did my cross multiply method for the math here. I have 8.4 and 0.48 and 0.35 and V. Crunch your numbers down, and I do get what I expected of a higher volume. Instead of 8.4 liters, I have 11.52 liters. So more direct relationships. So we've got Boyles, Charles, Gay-Lussac's, Avogadro's. All of those have something in common. All of those have paired data. 2 volumes, 2 temperatures, 2 pressures, 2 numbers of moles. The last one that I want to cover tonight involves something where we have only one of each. This is known as the ideal gas law. PV equals nRT. Now, when we looked at Boyles, it didn't actually specify what unit we had to use for pressure. And as long as the left-hand side matched the right-hand side, it doesn't actually make a difference. You can use torr or millimeters mercury or pascals or atmospheres. For Charles, okay, T has to be in Kelvin, but volume could have either been in liters or milliliters as long as you are consistent. The ideal gas law is much pickier. You need to have specific units in order to make everything come out the way it's supposed to. So our pressure must be in atmospheres. Volume is in liters. N for the number of moles, which is a decimal anyway. And then we have a number that we haven't seen before. This particular equation labels it capital letter R. It is known as the universal gas law constant. And for the purposes of this semester, because we are using atmospheres as our pressure, the number value that goes with this is 0.0821. Look at the units though. You can kind of think of this as, okay, it's the fudge factor. It's the magic hand-wavium factor that makes sure that everything else cancels out the way it's supposed to. Because the top of the unit is liters times atmospheres. The bottom of the unit is moles times Kelvin, which then means my temperature has to be done in Kelvin. But we did say already that for gas laws, all of the equations are done in Kelvin. We're also making some assumptions here that are not entirely true. Because it is called the ideal gas law, we are also making some assumptions that the gases are behaving a particular way. Now, as long as we are at an atmosphere or maybe a little less, okay, we're good to go, because normal, average, everyday lab situations are normally about 1 atmosphere. But the other thing that plays into this is, in reality, this only works well at relatively high temperatures. So we're making some assumptions that are not entirely true. However, it works pretty well from the calculation end of it. And even in the one lab that is up and coming next month, the assumptions have some minor corrections made when gathering your data, and the data still usually comes out pretty well. So if we have a sample, and I used a big sample this time, 9 liters, at room temperature, 20 Celsius, but kind of a high pressure, we have 4 atmospheres. How many moles are we talking about? So I need to do a little bit of tweaking here as I put things into the equation. I definitely need to convert my temperature unit over to Kelvin. So add your 273. So 4 atmospheres, 9 liters. N is my unknown. I have 0.0821 because that is my fixed value for my R, my 293 for Kelvin. Crunch your numbers, finish out your data there by dividing. I end up with 1.497 moles. So we have all these pieces of data that are sort of combining to give you this information. This gets us through about halfway or so through the chapter. Because homework is due tonight, are there questions about homework for chapter 4, the chapter that we finished on Tuesday?
Yes, I do. I have a question.
Okay.
So I'm on the last 3 on the back page, like number 13 and 15 have me stuck. So it's one that has like reaction. If you run the reaction with 556.6 of K2 PtCl4 and 34.6 grams NH3, and the reaction has a 95% yield, how many grams of PtNH3 to CLT will be produced?
So think about this in terms of, okay, if you calculate your 100% yield, that is your theoretical yield. However, when you are approaching it from the idea that it has 95% yield, you then need to make use of the 95% concept in order to multiply a decimal version of 0.95% times what your theoretical yield is. And that will allow you to make a correction that accommodates the fact that you didn't actually get 100% yield. Does that make sense?
It somewhat does. It explains a little bit more. So that means I'm not solving for 100% then.
You have to solve for your theoretical, okay?
Right.
Your theoretical is the initial portion there, okay? But once you figure out how much would have been produced if everything had gone perfectly, then you can take 95% of that as your final answer. You got to figure out which one is limiting, okay? The limiting is the key initial step there. Once you figure out what's one limiting, then you look at your balanced equation, which actually is kind of nice in that you get one product for every one potassium cisplatin. So it's kind of nice in that your relationship is 1-to-1 there.
Mm-hmm.
But you're still going to need molar masses to get your theoretical. Do your 95%. I would recommend doing it as your final step in the problem.
Okay.
There are a couple of additional examples that are not in my notes that are actually in your textbook that you can also look at those too.
Oh, they're okay. I'll look in the textbook.
Yeah, there are a couple. There are some stoichiometry examples there.
Okay. And then the last one there was like how many grams of product can be produced from 10 grams of NA.
Right.
So I balanced.
That one is you must balance the reaction. I gave you an unbalanced reaction.
Right.
If you do not balance the reaction correctly, you cannot do the normal 3 steps of stoichiometry.
Okay, so that's what it was. Okay,
Yes.
perfect. Well, that helps. Thank you so much.
Other questions regarding the homework set? Like I said, stoichiometry, okay, I've been doing this for a long time. Stoichiometry is a concept that a lot of people kind of have to dig their fingernails into. So I wanted to make sure that we had time to go over the answer key on Tuesday, which, like I said, pushes your test off to, I know it's the holiday weekend, but that's unfortunately the way the summer semester kind of tends to play out. And you'll have from Friday morning all the way until Monday at midnight to do the test. So if you do still have some weekend plans, you can probably do a workaround to help figure out what time you want to take it.
So the test is on the holiday weekend then?
Yes.
Okay.
Like I said, I think now the other 2 tests I haven't quite entirely figured out yet, but test 3 is probably the weekend of July 18th, and test 4 is probably going to be the final Tuesday of the semester, possibly. Or like from Tuesday night after class until Wednesday the following midnight, because we kind of get jammed up right at the end. And then there's a final exam, which really only has kind of about a 36-hour window, in which you can decide when you want to take it. 10 weeks always puts us in kind of a weird crunch at the very end. I will try to give you guys as much update information as possible as we get closer. So regarding lab, make sure you watch the videos that are attached to the document for the limiting reactant lab. I think everybody, I believe, has done the metathesis lab now, except for the couple people I know who are doing makeups next week. And then next week's lab is a titration lab, which involves the burettes that you got a little bit of an introduction to the first week of the semester. Other questions regarding lecture or lab? Otherwise, I will see some of you on Monday.